So if we discuss a physical, what physically it means if we use a Laplace transformation. So it converts motion into like motion in time. Basically it's convert motion in time into information. It doesn't deal with what is the position of car at t equals to 5 second, what is the value of x. It doesn't deal with this one. Rather it converts the whole vibration motion into information about decay or growth, how much decay and growth makes up the total vibration of the system, oscillation, stability of the system. So the Laplace transform is not going to give you information particularly about the, let's say, what's the position of a system at time equal to 10 seconds. Rather it will give you the holistic view of your motion, like part uh, how much part of the total vibration is made up of the growth and the decay, and how much part is the steady state part of your vibration, and what's the stability of your whole system. So this is what information you will get from the Laplace transformation. I will explain with some examples. So we will start with, let's take an example of car. For example, a car is, oh, just we just draw a car. Let's say a car is going along a road, and you have you may have different kind of speed breaker. You may have a very sharp edge speed breaker like this one, that is stopping the car, and you may have a kind of a jump type speed breaker like this one, and you may have seen at some places you have consecutive small jumps like this one. So let's say a car is moving along a road and you have these kind of jumps along the way. So maybe this give uh, this excites the car with a sudden sharp hit. It will, let's say, add an impulse force to the car. It will apply the impulse force to the car. If a car reaches on this one, second one, it may apply the kind of step force. And if you may have, if the car encounters passes through this speed breaker, it will apply kind of a sinusoidal force of a particular frequency. So at a particular frequency the force will be applied onto the car body. So let's say, so at time before t equals to 0, the car was smooth, there was no vibration. At t equals to 0, the wheel hits any of these bumps, so there was an input, force acts onto the body, and after t equals to 0, or you can say t greater than 0, the car body starts to vibrate. Vibrates and resettles. So let's say f of t was the force that was applied onto the car. So if we were analyzing the system in the time domain, so we would have a different type of solution. We will be making transient and a steady state motion. We will be analyzing it separately using a homogeneous of the particular solution. So the time domain will let us information we will get from the time domain. What's the displacement at every time instant. This is the information we will get if we use the time domain method using the general solution method. uh, Obviously this is hard for the irregular forces. You may find it for the regular force, but it's hard for irregular forces. You may have a ramp force as well. But if we use the Laplace method or the frequency domain, you can say Laplace deals with the frequency domain. Laplace transformation, it will tell us what amount of exponential decay, or you can say damping and oscillation. So it's not concerned with the position of the car at any time instant. It is concerned with the various information of the holistic view of the overall motion of your car, growth or instability. So this is how we can differentiate between the solutions of the general solution method and the Laplace transformation. Take another example of, let's say, sound example. Let's say music. So there's a music playing on a radio. Let's call it f of t. Let f of t be that song or the music. So in time domain, you will hear the music changing with the time. uh, like the amplitude of the music is changing with the time, and the intensity of the music is changing with the time. Sound intensity, like amplitude of vibration changing at every instant. While for the Laplace transform, so the Laplace transform, you will be able to get the information how much is base of the sound, how much is the mid, how much is the treble. So it will analyze you, like, for the total music duration of that sound that is coming out from the speaker, how much is the bass part, how much is the mid, how much is the treble part. So it will give you the information of the whole uh, that soundtrack, instead of letting you the or giving you the information about the amplitude of vibration at every time instant of the particles of the air or the film of the speaker that is making the sound. So we are not concerned with that. We are concerned with how much is the bass in the mid and treble. Let's say the time domain will tell you what is a sound at 3.2 second, but the Laplace transform will tell you what were the ingredients of that makes those sound. So you know these are the ingredients, how much is bass, how much is mid, how much is treble. So this is how you will be able to analyze the Laplace, the systems using the Laplace transformation. So just look at it differently. Don't compare them. Don't compare apple with mangoes. So they are two different techniques used for two different purposes. Although we can use the inverse Laplace transformation to go back into the time domain and get the information related to the time with the changing time. But the main purpose of this one is to get the information of the holistic vibration pattern. Uh, and you will find that Laplace transform, it uses uh, e exponent minus s of t. That's common Laplace operator. So the s is a complex variable of Laplace, which is equal to gamma plus sigma plus iota omega. So the s itself, it tells if it is large value. Let's say if s is large, motion dies quickly. You will see the mathematical part of this one as well. If s is small, motion lasts long, and if s has imaginary part, if s is imaginary, uh, system oscillates. Sorry. So and so this is how we can the Laplace operator that will this is how we can get different information from the Laplace operator. That's all for the basic explanation for the Laplace variables and the Laplace transformation itself. So we will start with the explanation of the Laplace transformation for different functions. So let's define the Laplace transformation. So let's suppose we have a function f of t, which is any function, a time function you can say. Such that f of t is 0 for t less than 0. Means before you start observing the system, no force was applied onto your system. So this is what it means. And we have s complex variable. I have introduced this before. And we add a strange looking L. It's just a Laplace operational symbol. It just shows that we are performing the Laplace transformation at this step. Operational symbol you can say. So by the Laplace integral, it operates it tells about the quantity upon which it operates to be transformed the Laplace integral, which is equals to 0 to infinity e exponent minus st dt. That's a Laplace operator I told you earlier. And f of s is the Laplace transformed function when f of t has been converted into the f of s. So it's Laplace transformed function you can say. So let's say we are performing the Laplace transformation of any function f of t. So it becomes equals to f of s, and we can write it as 0 to infinity e exponent minus s of t dt. And so we are just multiplying this Laplace operator with the f of t. So we will have this is what we'll got after transforming the function into the Laplace transform function. So now we can just perform this integral and get our final value. And if you want to get it back, we will perform the inverse Laplace transformation. We will see that later. So let's take an example. Consider the of some basic function. Let's start with the exponential function. Let's say we have a function f of t equals to 0 for t less than 0. That's basic condition for the Laplace, for the function that can be Laplace transformed. And f of t equals to a, which is any constant value exponent minus of alpha t for t greater than equals to 0. So any force is applied and that function has this value. So a and alpha are constants. So now if you want to perform the Laplace transformation of this function, it will be a e exponent minus of alpha t. So this become 0 to infinity. We just have to multiply it with our Laplace operator function. So it will be a e exponent minus alpha t into e exponent minus s of t dt. Now this is the Laplace transform function. Now we have to solve it. So since a is the constant value, we can take it out of the integral. It becomes a 0 to infinity, and you can combine these two exponents together. So e exponent minus of alpha plus s t dt. So from here, from the integral properties, integral of the antilog, it will be equals to a divided by this comes into the base, it will become s plus alpha. That's an integral property of the antilog. So now f of s is you can say, so you can rewrite it as the Laplace transformation of a e exponent minus alpha t is equals to a divided by s plus alpha. We can take example of another function. Let's say that's for the exponential function. Let's take an example of step function. What if our force is kind of step force? So step force is like there was no force at 9, and then let's say time t equals to 1 second, you apply the force of magnitude a. So that's the step force. So again, you can write it as the function is equal to 0 for t less than 0, but the force or the function is equals to a. That's simple a, there's no exponent involved, it's a step force for t greater than equal to 0. So as soon as that you start observing, you apply the step force that has a magnitude of a. Now you can perform the Laplace transformation of this one. It's equal to 0 to infinity a multiplied by e exponent minus s of t dt. And since a is a constant value, you can take it out. What we are left with is 0 to infinity e exponent minus s of t dt. And since this is equals to 1 over s, so it becomes a over s. So the Laplace transformation of any step force is equals to a by s. A can be any amplitude. Let's say a is 1, it's a unit step force, it becomes 1. Take another example of ramp function. Ramp function or ramp force. I'm just using force again and again just because you will be dealing with a force in this whole course. You are applying force onto your system. So consider f of t again equal to 0 for t less than 0. There was no force before you start observing, but for t equal to or greater than 0, the function is a into time. So what it tells, as soon as the time starts, you start observing, the amplitude is increasing like this. So with the time, you have a constant value. Let's say a is equals to 2. So at 0 is 2 into 0 0, At 1 second, 2 into 1 it's 2. At 2 seconds, 2 into 1 it's 4. Then at 3 seconds, 2 by 3 6. It's like this one. This is how the ramp function works. It's kind of a slope at 45 degrees. uh, I'm just giving a simple example. So this is the ramp function. Now you can perform the Laplace transformation of this ramp function. The Laplace transformation of ramp function at would be equals to 0 to infinity, again at e exponent minus s of t dt. Now that's a bit complex than the previous one because you have t on at the bottom. So we have to apply the multiplication rule of integration. So again, first simplify it, take a out, become a 0 to infinity t exponent e minus s of t dt. Now you can apply the multiplication rule, so it becomes a t u into integral of v, that's become e exponent minus s of t dt, plus e exponent minus s of t into integral of t dt, and then you can solve it in this way. So for this one you can write it as a 0 to infinity t e exponent minus s of t dt. This becomes a and t e exponent minus s of t divided by minus s, 0 to infinity, that's a condition, minus 0 to infinity e exponent minus s of t divided by minus s dt. And you can further solve it, a over s 0 to infinity e exponent minus s of t dt, it will be equals to a over s square. So the Laplace transformation of a ramp function is equals to a over s square. You can perform the same for the sinusoidal function as well. All you need is just to use a basic theory of the integral function, integrals. So this is how you can find the Laplace transformed function, and then you use that in your vibration systems. So next we will try to solve a few systems using the Laplace transformation. But before going to that, I will share some details. Where is it? I will share a graph or that a table which has it has already given you the Laplace transform values of every function. So if you have a function like this one, its Laplace transformation is equal to this. If you have a function like this one, its Laplace transformation is equal to this. If it is sine omega t, its Laplace transformation is this. So they have generated a table for you so that you don't have to calculate again and again. You can just directly refer to this one. You will be allowed this table in your examination as well. It is better to uh, like memorize some general or commonly used like sine omega and t and e exponent minus at, but you don't have to memorize all of them. You will be allowed this table in your examination. Before going to that, we will see how the Laplace transformation of differential equation takes place, because we have seen the Laplace transformation of force function, because we know when we are dealing with the vibration system, we will have equation like uh, mx double dot plus cx dot plus kx equals to f of t. So now we know how to perform the Laplace transformation of this one, but we don't know how to perform the Laplace transformation of these functions. So the integral part is solved slightly in a different way, and for that we will see the differential theorem for the Laplace transformation. So let's say if we have a simple differential values for the Laplace. I apologize for some messy notebook today because I'm not using my pad. I'm using some other device for recording the lecture, so it's not very organized like in the last lecture. So how to perform the Laplace transformation of derivatives? So let's say you have a function d over dt of f of t, and you want to perform the Laplace transformation of this function. So it will become when you perform the Laplace transformation of any function f of t, it becomes f of s, right? So let's say if you have a single derivative, it can be transformed into the Laplace transform function equals to s, because you have a single derivative, into f of s minus f of 0. That's an initial condition. Let's say if you have a double derivative, d over dt square f of t, it will be equals to s square f of s minus of s into the initial condition minus of into the first derivative of initial condition. Let's say displacement of the velocity, and you can continue this so on and so forth. So let's say if you want to do for x double dot Laplace transformation of x double dot, it will be equals to s square x of s minus s x of 0 minus x dot of 0 at that time t is equal to 0. And you must have these initial condition in your question statement, the problem statement. Sorry, let's say 5 meters, and let's say time to 0 2 meter per second. So you will have these conditions provided in your problem statement. So this is how you can perform the Laplace transformation of the derivative. So I'm not going into much details for this one because that's purely a mathematics topic. I just explain it in the beginning so that whenever you are solving the mechanical vibration systems, so you don't end up getting stuck with the fundamental theory of the Laplace transformation and what the physical meaning behind those Laplace transformation. So now our next attempt would be to solve a problem using a general solution method and using the Laplace transformation method. So just you can compare how efficient the Laplace transformation method is compared to the general solution method. So let's jump on to that.